Balancing and classification of reactions. All right, so we've seen balanced chemical equations. We just haven't really looked at them explicitly yet. So let's practice them. So molecular hydrogen reacts with molecular oxygen to yield water. So we should recognize it's just saying hydrogen reacts with oxygen to make water. But there's a couple things we have to remember. Remember the diatomic elements, so H2O2, right? Have no fear of ice cold beer. So molecular hydrogen means this. O2 is molecular oxygen. And what form, right? What phase do we typically find hydrogen as a gas? So we'd write H2 gas plus O2 is also a gas, yields water. Now here we'd have a choice whether it's liquid or gas. And that's going to depend on the temperature and pressure conditions, but let's just say it's liquid. All right, so here we have, right, we read this as hydrogen reacts with oxygen to give water. An important thing with a balanced chemical equation is that you have the same number of atoms of each type on both sides. So on the left, we have how many hydrogens? We have 2 hydrogens. How many oxygen atoms do we have? 2 oxygen atoms. On the right, we have 2 hydrogen atoms, but we only have 1 oxygen atom. That's not balanced. So the only way you're allowed to, what you're allowed to do when you balance is put coefficients in front of the elements or compounds, right? You can't put subscripts or superscripts in anymore. So what I'm going to do is I'm going to double this guy. So now I have how many? I've got, start again, now I've got 4 H's, right? 2 H's, but 2 waters. All right, so if I drew this as a Lewis structure, it would look like this, right? How many H's do I have? 4. How many O's? 2. Okay, so that's good. Over here now, I have 2 O's, so that's good, but I only have 2 H's. How do I fix that? All right, I just put a 2 in front there. All right, so this is a balanced chemical equation. All right, it's balanced for charge, which we haven't talked about yet. It's balanced for the number of atoms. They're equal on both sides. And we write these states, the phases of matter. So things can be solids, liquids, gases. Aqueous means you're dissolved in water. Right, so you can't write H2O aqueous. That would mean water is dissolved in water, and that's just silly. So water can be a liquid or a gas, but for example, sodium chloride, if it's dissolved in water, would be aqueous. Heat is shown as a triangle, right? If I wanted to heat up a reaction, I can draw a little triangle on here to say I'm adding heat to that system, and I can put catalysts in there. So let's say I put a palladium catalyst or something. We'll talk more about these. All right, here's another one. So you should give this a try. It says propane gas burns in oxygen gas to form carbon dioxide gas and water vapor. You in there like a Canadian. All right, so pause me and give it a shot. You didn't pause me. I'm serious. You have to think about these things. All right, so propane gas, C3H8, burns in oxygen. Just means it sees oxygen. Remember, O2 is elemental. Or it's a diatomic, and it makes carbon dioxide, gas, it tells me, plus water, vapor. Vapor means gas. All right, I've included everything there. Now we have to balance it. Oh man, what do we see here? So I got 3 carbons. So let me try 3 carbons here. Okay, 3 carbons, 3 carbons. That's good. H8, I have 8 H's here. Now I only have 2, so I'm going to put a 4 in front of here. Now that's 8. Whoops, that's 8, isn't it? Okay, let's do O's now. On this side I have 6. This is 6 O's, right? 3 times 2 O's is 6 O's. 4 times 1 O is 4 O's. That's a total of 10 O's. And 10 O's on that side. How many O's do I have? 2 here. So if I put a 5 here, oh, what happened? I didn't write this as gas. Gas. 10 O's. I think I did it, didn't I? Now, just go back and check it, right? There's no reason to ever get these wrong. 3 C's. 3 C's, right? 3 goes to that guy. This means 3 CO2s, right? So that's 1, 2, 3 C's. H, I have 8. Over here, I have 4 times 2, which is 8. Check. And then finally, O's again. We said 4. Stop it. 4 O's plus 3 times 2 is 6 O's is 10 O's still. Nice. And 5 times 2 is 10 O's. Balanced. Nice work by us. Did I get the phases right? Gas, 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 gas. Yes. Nice work by me. Let's take a look at different kinds of reactions or ways to describe reactions. There's kind of two different approaches. One is you look at the number of products and reactants, right? The stuff on the left and the stuff on the right, right? Reactants here on the left, products on the right. Or you can look at the kind of chemical reaction, right? Are things coming together to make precipitates? Are they acids and bases reacting? Or are they electrons being moved around? All right, we'll talk about precipitation reactions, acid-base reactions more in part 5. We will talk about redox here. But let's take a look over here. Oh, that's nice. All right, so decomposition, you start with one thing and you make two things. All right, why couldn't I do this? All right, this goes all the way back to part 1 where we talked about the conservation of mass and Dalton's laws of atomic theory, or Dalton's atomic theory, right? You can't just change B into C, right? The parts we have available stay consistent. Combination means I take things, could be two things, could be three things, and I combine them into one thing. Single displacement, sometimes people say single replacement. I have something and a compound, right? A single element and a compound. And you can see that they switch partners. So B was paired with C. Now A is paired with C and B is alone, right? They're displacing each other. And then double displacement means you have two compounds and they both change partners, right? An important thing is, remember with compounds, this is most likely going to be, well, if they're ionic compounds, the cation goes first and the anion goes second, cation, anion. So this is still cation, anion, right? You wouldn't go, this makes BD, right? That would be an anion and an anion, and that would be ridiculous. Okay, so we can describe these things in terms of the number of products and reactants. One thing going to two things going to one thing in a compound going to a different compound in one thing, and then switching partners, right? Decomposition, combination, or metathesis, single displacement, double displacement. Or we can talk about the kind of chemistry. And give me some examples. So combination reaction. Remember, this is things coming together to make one thing. So A plus B comes together to give me C, something different in this case, right? These aren't atoms, these are compounds now. So here's an example. Here, aluminum reacts with bromine to make aluminum bromide. All right, is it a balanced chemical equation? Two aluminums, 3 times 2 is 6 Brs. 2, remember this is 2 AlBr3s. This means this, doesn't it? So there's 2 aluminums and there's 6 Brs, isn't there? Okay, but that's combination. Two things came together to give me a new thing. The new thing can fall apart to give me its component parts, right? That's a decomposition reaction. Yeah, interesting. All right, and here we have a balanced chemical equation. Single displacement reactions, remember we have one thing displacing somebody in a pair, right? So A is kicking B out. Now he's the pair and B is all by himself. And here are some examples. So there's metal displacement, where I have a metal that's interacting with chlorine, right? So it's a titanium chloride, wrong button. Titanium chloride, right? Now who has the chloride, right? Titanium had it on the left, on the reactant side. Now magnesium has it. That's metal displacement, a single displacement reaction. Here, potassium is forming a compound with bromide, but now potassium is forming a compound with chloride, single displacement. This one looks a little weird, but we can think of it this way. So here, H is forming an interaction with OH. Over here, who's forming the interaction with OH? Right, so it's a displacement reaction that way. And you'll notice that, right, the diatomics remain diatomics, right? They're not diatomics when they're ions, but when they're elemental, behaving as molecules, they'll be diatomic. Classic. All right, double displacement reaction, right? So switch partners. And remember, most of the time, the cations, it'll be ionic compounds, many of the times, unless it's acid-base. But the cations stay cations, the anions stay anions, right? You wouldn't want to mix them up. You would not make DB, right? So precipitation reactions, we've seen these in lab, right, with our barium sulfate reaction. Two aqueous solutions, right, are mixed to form a solid. Classic example is lead 2 nitrate mixed with potassium iodide. So here's lead 2 nitrate, right, because he has a +2 charge. Aqueous means he's dissolved in water. He's clear and colorless when he's like that. Sodium iodide is also aqueous, dissolved in water. It's also clear and colorless, maybe a little hint of yellow. And it reacts, they switch partners, right? PB is now paired up with I, and NO3 is now paired up with Na. So I put those together, right? Okay, lead 2 iodide is a solid, sort of a bright yellow solid. It could be this. And if they spin it down, you can see it precipitates to the bottom. Okay, so classic example of a precipitation reaction. Another kind of double displacement reaction is the acid-base reaction, where an acid reacts with a base to make a salt and water. In this case, hydrochloric acid reacts with sodium hydroxide, making sodium chloride, right? This is salt and water. So remember, any ionic compound can be described as a salt, right? So KCl is a salt, sodium sulfate is a salt, but salt is sodium chloride, right? Table salt. Okay, and so from a molecular basis, HCl reacts with NaOH. We have H plus ions, chloride ions, sodium ions, and hydroxide ions. H plus reacts with OH minus, chloride reacts with sodium, so you get sodium chloride, and you should get H2O, which is what this is. Here's a fun, why do we not like this? This is, I don't know where I got this thing, well, Shutterstock, fail. And bad work for me by copyright infringement. But nonetheless, O would have a 2 minus charge, wouldn't it? H has a positive charge, and if there's 2 of them, I put a 2 in front. But really, it's going to be H2O. They're no longer ions. It's going to be HOH, right? A nice molecular compound. All right, so decomposition, combination, single displacement, double displacement. We saw precipitation reactions and acid-base reactions. And so that leaves redox reactions here. And so redox reactions are electrons being transferred. Okay, so some terms we're going to learn. Oxidation is the loss of electrons. Reduction is the gain of electrons. And there's some mnemonics for that. Do you know any? Most people know oil rig. All right, oil rig. Oxidation is losing. Reduction is gaining. I prefer Leo says Gur because lines are cool. Lose electrons, oxidation. Gain electrons, reduction. Either way, it's true. Okay. A definition we need to know is that reducing agents donate electrons, right? They are oxidized. Right? They donate the electrons to the other guy and are oxidized. Oxidizing agents do the opposite, also called oxidants. They accept the electrons and are reduced. So know these definitions. And we're going to practice doing this next. And to do that, we need to know something called the oxidation number. So it turns out that the oxidation number of solid magnesium, and we don't need to know this yet, is 0. Oxygen as an elemental form is also 0. As ions, or as an ionic compound, the oxidation number is the charge on the ion. All right, we know from the periodic table, magnesium likes to form a +2 ion. Oxide is a -2 ion, right? If this guy becomes more positive, that's oxidation. If this guy becomes more negative, that's reduction. But when we see that these oxidation numbers change, we recognize that it's a redox reaction. We'll talk more about that next time.